It looks like ordinary matter, has the same chemical properties, except if I touch it, it would explode.
The renowned Large Hadron Collider at CERN, located close to Geneva in Switzerland, came back to life in April 2022 after an astonishing 3-year outage for substantial repairs and maintenance. This historic occasion signaled the beginning of the unprecedented scientific project known as Run 3, which promises a succession of mind-blowing tests planned to capture the interest of the globe until 2024. The activation of the renowned Large Hadron Collider, however, has just been the subject of yet another worrisome revelation from CERN. What is the latest discovery that LHC at CERN has just exposed? What is the importance of LHC in the field of particle physics? You will get to know this and plenty more about it as we dive into the details of today's show. However, before getting started with the video officially, here's a quick reminder that you can subscribe for free and like the video so that we can boost the algorithm. Comments are most welcomed. Organizations like NASA, Tesla, and countless more are drawn to the never-ending quest for information about our planet. The European Organization for Nuclear Research delves into solving the riddles of Earth and revealing its latent potential, while NASA and Tesla concentrate on space exploration. The world's largest and most prestigious scientific research facility, CERN, employs scientists, physicists, and engineers in its effort to provide solutions to some of science's most vexing problems. Their research ranges from examining the dark matter and extra dimensions to diving into speculative ideas. These endeavors are supported by complex and cutting-edge scientific tools that are beyond comprehension. Even while CERN has made groundbreaking findings like those involving neutral currents, the Higgs boson, and the elusive God particle, there is still a hunger for more information. The hunt for magnetic monopoles is one of CERN's current projects. In contrast to ordinary magnetic particles, which have both north and south poles, magnetic monopoles only have one of the poles. Magnetic monopoles have evaded scientists' detection for a century, despite their theoretical existence. Colliders have been created as a result of this endeavor. Colliders are designed to produce particle collisions so that researchers can examine the after effects and learn important lessons. Although monopolies were supposed to be produced by colliders, none have been discovered thus far. The Large Hadron Collider was built by CERN with the goal of discovering new particles such as monopoles. It is a massive particle accelerator that boosts subatomic particles to extremely high energies to enable study of them through carefully orchestrated collisions. Particle colliders essentially smash atoms to reveal the mysteries within. The particles must be electrically accelerated before colliding. It does this by speeding up particles close to the speed of light. Strong electromagnets are used by the LHC to generate a magnetic field that is over 11,000 amperes strong. It has a superconducting coil that guarantees less energy loss during current transmission. The LHC is built with sturdy concrete walls and is roughly 328 feet below ground. It was carefully positioned to reduce background radiation from the Earth's crust. These characteristics enable the collider to produce magnetic fields that are roughly 1,000 times stronger than the magnetic field of the Earth. Thousands of lattice magnets are used in the accelerator to modify particle paths. The LHC is essentially a 27-kilometer ring of superconducting magnets with dipole magnets that have been specifically engineered to bend particle pathways. The immense magnitude of the LHC becomes obvious with over 1,300 dipole magnets weighing 35 tons each and measuring 15 meters in length, requiring substantial investments of time, money, and resources. Currently, the LHC is still in use, advancing knowledge in the quest to comprehend our cosmos. The world's most potent collider, the Large Hadron Collider, LHC, is a remarkable scientific achievement that accelerates trillions of particles at astonishing rates. Accelerators are used to direct proton beams in opposing directions so that they collide with one another, enabling groundbreaking discoveries. The scientific world celebrated the LHC's successful completion of the European Union's mission to advance our understanding of the cosmos after 3 years of waiting. The LHC was painstakingly built over many years and immediately proven to be a great instrument for scientific research. It was a difficult effort to build a complicated machine. The LHC's high-energy collisions provide researchers a unique understanding of the complex structure of the subatomic world. Even though smaller particles collide naturally every day in our atmosphere, the resulting product soon decays, making it difficult to directly study them there. The only way to effectively explore them is through the massive tube of the particle collider. One of the most expensive scientific equipment ever created, the construction of this majestic structure lasted from 1983 to 1988 and cost roughly 7.5 billion euros or $9 billion. The LHC and its simulations produce approximately 600 million particle collisions every second. or 15 petabytes, 1,000 terabytes of data annually. For CERN experts, reviewing such a massive amount of data presents a tremendous challenge, which is why the LHC is a cooperative project including scientists from many nations. Although the LHC started running on September 10, 2008, the initial testing phase was delayed by more than a year due to a magnet quench event. Over 50 superconducting magnets and their parts were damaged as a result of the incident. The LHC finally had its chance to shine in 2010, when protons and lead nuclei collided at incredible energy, revealing previously unobserved scientific phenomena from 2010 to 2013. The voyage didn't finish there, though. The CERN researchers understood that this super collider needed to be improved further. Consequently, the LHC underwent a 2-year refurbishment called Long Shutdown 1-inch LS1 in 2013, a temporary shutdown, and a restart in 2015. The LHC was upgraded during this time, along with its accelerators, detectors, and some magnetic systems. As a result, the LHC can now work at full capacity and has shown itself in the wonders of particle physics with noteworthy discoveries and experiments. As a result, the LHC awoke in 2015 with enhanced capabilities, continuing to push the boundaries of scientific inquiry and opening up new paths for human understanding. Let's dive into some of the discoveries of LHC. Unprecedented subatomic particles. The standard model of particle physics frames the world of subatomic particles as we currently understand it, a hypothesis that describes the interactions between the fundamental particles. The LHC's discoveries have made it difficult to broaden this same framework, though. The discovery of previously unobserved subatomic particles is one such revolutionary revolution. 2020 saw the discovery of a brand new variety of tetraquarks, an unusual 4-quark state of matter, according to the LHC-B experiment run by CERN. Protons, neutrons, and other particles can be created by combining quarks, which are fundamental particles. Particles composed of 3 quarks are found in the conventional matter and come in 6 flavors: up, down, charm, strange, top, and bottom. Protons, neutrons, quarks, and antiquark pair mesons are examples of baryons. This fundamental rule is defined by the discovery of quark-based particles, which opens up new possibilities for particle physics research. Moreover, the LHC-B experiment in 2015 found a pentaquark made out of 5 quarks. The LHC experiments were the first to unambiguously identify this particle, which had been anticipated by theorists. This unexpected discovery introduced a completely new class of particles by upending the conventional wisdom of how quarks can interact with one another. Additionally, the ATLAS and CMS experiments at the LHC found evidence of a fresh Higgs boson decay mode into muon pairs. This discovery is significant because it offers a rare chance to thoroughly examine the Higgs boson's characteristics. This is a surprise and significant discovery because the muon is the electron's heavier relative, and the likelihood of the Higgs boson decomposing into muons is quite low. These LHC discoveries show that the subatomic world is even more intricate and intriguing than our current models imply. We are forced to reconsider our existing knowledge of particle physics when we discover these new particles, which may require us to revise the standard model. These discoveries serve as the proverbial tip of the iceberg of the unknown, a glimpse of the vast number of particles still lying dormant. Each has the capacity to challenge our preconceived notions of the cosmos. Dark matter particles. For decades, scientists have been intrigued by the mystery of dark matter, an unexplained element of the cosmos that does not interact with light or any other electromagnetic radiation. The precise makeup of dark matter is still unknown, despite the fact that its presence has been inferred from its gravitational effects. However, the LHC is presenting fresh chances to maybe find and comprehend dark matter particles. Dark matter particles are being produced for direct observation in experiments at the LHC. The generation of these elusive particles would be inferred from the imbalance of momentum and energy in a particular collision event, an effect that is frequently referred to as missing energy, even though they would pass by the LHC detectors undetected. While the ATLAS and CMS consortia did not discover a smoking gun for dark matter particles, their results from searches for novel physics processes with big missing energy in 2020 represented a significant advancement in the quest for dark matter. In addition, scientists are looking into the potential that the Higgs boson might serve as a gateway to the dark sector. Since the Higgs boson can change into other particles, under some circumstances it may decay into dark matter particles. The decay would result in an apparent energy imbalance that might be monitored, even though these particles would be invisible to our detectors. These LHC research areas are among the most fruitful in the worldwide search for dark matter. It would not only be a monumental discovery in and of itself if dark matter particles were detected at the LHC, but it would also have significant ramifications for our view of the cosmos. It would be possible to find new physical forces and laws if it were determined that dark matter is a particle. The function of the LHC in this investigation defies reason as it explores uncharted areas of the cosmos in an effort to detect the undetected and make the unseen visible. Quantum superposition breakthroughs. Quantum theory, the theory controlling the microscopic world, is renowned for its peculiarity at its core. The superposition principle is one of quantum physics' most baffling concepts. Until it is detected or measured, the superposition principle argues that a quantum system can exist in several states simultaneously. Schrödinger's cat, a famous thought experiment, serves as an illustration. Until noticed, the Ray cat in a box could be both living and dead. By seeing a related occurrence in subatomic particles, scientists have made progress in comprehending quantum superposition at the Large Hadron Collider. They have specifically been looking into the strange world of mesons. The D0 mesons, which can exist in two states simultaneously and mimic the concept of quantum superposition, have been the subject of a thorough examination by the LHCb experiment. The D0 particles are found to oscillate between two states, according to researchers. The LHCb team was able to measure a parameter known as the mixing phase, which provided a new perspective on the superposition phenomena. Researchers now have the opportunity to verify the CP symmetry postulate of quantum mechanics, which establishes the fundamental physical rules. According to C symmetry, a particle's antiparticle should replace it, and according to P symmetry, a particle's spatial coordinates should be turned around. The reason matter dominates antimatter in the universe may be understood through deviances from this principle. Unraveling the mysteries of antimatter. The matter-antimatter asymmetry is one of the deepest mysteries in the cosmos. Equal proportions of matter and antimatter should have been formed at the beginning of the universe, according to the Big Bang theory. But given that matter now clearly predominates in the universe, what happened to all the antimatter? The Large Hadron Collider has made considerable advancements in solving this conundrum, which is at the core of one of the most difficult problems in physics. In order to understand why the cosmos is primarily made up of matter rather than antimatter, the LHC Beauty experiment in particular is intended to investigate the characteristics and behavior of particles containing a beauty quark or B quark. Researchers at the LHC have been carefully examining particles known as mesons. These particles have the ability to oscillate between their matter and antimatter counterparts and decay into other particles in ways that may show potential matter-antimatter asymmetry. The LHCb experiment has discovered some notable discrepancies between the decay rates of some B mesons and their antimatter counterparts, which suggests a breach in the charge parity CP symmetry. In addition, the LHCb has uncovered a novel charm quark-based asymmetry. The experiment discovered a previously unrecognized discrepancy in the masses of a particle known as the D0 meson and its antiparticle. This may add to our understanding of the riddle surrounding matter-antimatter symmetry. These known asymmetries, however, are still insufficient to explain the predominance of matter in the cosmos, indicating that there must be further sources of CP violation that have not yet been identified. The search for answers to the fundamental puzzle of the asymmetry between matter and antimatter is ongoing, and the LHC is giving us important new information. New dimensions. 3 spatial dimensions and 1 of time form the foundation of our understanding of the cosmos. However, what if there were more dimensions than our senses could detect? This is a serious theoretical physics claim, not just something from science fiction. A certain theory, such as the string theory, argues that there are more spatial dimensions. Some of the most significant physics mysteries may have solutions in these additional dimensions. Dark energy, dark matter, and the fundamental unity of forces are all discussed, and the LHC has been at the forefront of investigating these hypotheses in search of proof of more dimensions. These dimensions are not directly visible to us, but their effects on the energy and momentum of particles that we can measure can suggest that they exist. One strategy used by physicists is to search for evidence of gravitons, fictitious particles connected to the force of gravity that is said to have escaped into additional dimensions. Gravitons are a vital indicator of the existence of other dimensions since, according to some ideas, they can freely migrate across all of the dimensions mentioned. Gravitons would leave behind a clear signature in the form of lost energy if they were created in high-energy collisions at the LHC and then fled into additional dimensions. Furthermore, If the behavior of the Higgs boson deviates from these standard model predictions, this could provide indirect evidence of extra dimensions, which could change the properties of the Higgs boson. While researchers at the LHC have not yet discovered concrete evidence of additional dimensions, they have placed strict limitations on what might be considered about them. This pursuit profoundly challenges our concept of space and time by exploring areas that go against our preconceived notions of the cosmos. Exploring these absurd concepts continuously pushes the limits of our knowledge, as seen by the LHC's continual search for additional dimensions. We are getting a little bit closer to understanding the structure of the universe thanks to the work of LHC researchers. Higgs boson oddities. A fundamental particle in the standard model of particle physics is the Higgs boson, sometimes known as the God particle. It was found at the LHC in 2012, and for this finding, a physics Nobel Prize was awarded in 2013. The Higgs field, an essential component of the universe that gives other particles their mass, is connected to the Higgs boson. Since the Higgs boson's discovery, researchers have examined its characteristics to validate its anticipated qualities and search for variations that might indicate novel physics. In spite of the fact that the Higgs boson largely operates as predicted by the standard model experiment, the LHC has discovered several surprising characteristics. For instance, the CMS and ATLAS experiments discovered that the Higgs boson can decay into two muons, an extremely unusual occurrence that was discovered more frequently than expected. More information is needed to corroborate this conclusion, which might indicate the existence of new physics outside the realm of the standard model or statistical fluctuation. The apparent tendency of the Higgs boson to interact with heavier particles is another surprising finding. The strength of the Higgs boson's interaction with a particle should be inversely correlated with that particle's mass, according to the standard model. The top quark, the heaviest known particle, and the Higgs boson appear to interact more forcefully than anticipated, according to data from the LHC experiment. Finally, researchers are looking at the possibility of the Higgs boson decaying into unobservable particles, which would be a sign of novel physics like dark matter. Although the search for these putative decay continues, no evidence of them has yet been found. Although they are still being investigated, the Higgs boson's unique behaviors could have significant effects. They might offer hints to new physics that go beyond the mainstream model and shed light on the characteristics of dark matter. As scientists continue to screw up, the Higgs boson at the LHC is denied by the unification of forces or even the existence of additional dimensions. They are certain to find more surprises that contradict what we now know about the cosmos. Potential black hole production. The prospect of creating black holes at the Large Hadron Collider is one of the most shocking and contentious theories related to it, but huge cosmic phenomena like black holes are more commonly thought of. According to some hypotheses, high-energy particle collisions like those that take place at the LHC could result in the formation of miniature black holes. According to general relativity, a considerable quantity of energy must be concentrated in a very compact space for a black hole to form. While the energies attained at the LHRC are impressive on a microscopic scale, they are insufficient to create a black hole according to accepted physics. However, the existence of additional dimensions, as postulated by some theories like string theory, would lower the threshold for the formation of black holes, allowing them to form at energies comparable to those attained in the LHC. Theoretically, the creation of these tiny black holes at the LHC may show that there are additional dimensions or quantum gravity effects which could fundamentally alter our view of the cosmos. These black holes, if created, would be extremely unstable and are predicted to instantly decay into particles that can be found in LHC studies. Micro-black holes have not yet been seen in the LHC data. Experimental searches have mostly concentrated on finding events that may be a hint of black hole decay, since they have several high-energy particles in their final state. Researchers have been able to place restrictions on the likelihood of black hole generation at the LHC thanks to the non-observation of such occurrences. Although it may seem improbable or even unsettling to think that the LHC may create black holes, it is important to understand that even if they did, there would be no danger. We would gain essential knowledge about the underlying rules of nature from these tiny, short-lived creatures. Despite confounding common sense, the continued search for miniature black holes is pushing the bounds of knowledge. The continuation. The Large Hadron Collider, LHC, did, however, experience another shutdown in 2018 to execute improvements intended to increase its luminosity. The rate of collisions in a collider, known as luminosity, is a key element in obtaining scientifically significant data. The LHC's operating company, CERN, aim to probe deeper into the mysteries of monopolies and dark matter, two ideas well known to fans of science fiction. Dark matter is a class of substances that exists in space and has characteristics like the inability to absorb, reflect, or emit light, making it invisible to light-detecting technology. Dark matter is thought to have formed soon after the Big Bang, according to scientists. One of CERN's main goals for the improved LHC was to unravel the mysteries of dark matter. But instead of producing a breakthrough, the LHC produced unanticipated results that were contradictory to predictions. In April 2022, the LHC was restarted with the increased maximum beam energy, and CERN researchers made a startling finding about the Earth's magnetic field. Upon turning on, the LHC discovered a hitherto unrecognized phenomenon, an unusual fracture in the Earth's magnetic field. The north and south magnetic fields of the Earth generally exhibit polarity opposition, which causes a partial cancellation and the formation of a tiny gap at the equinoxes. But this one crack stayed open for an incredible 14 hours straight. The Earth's magnetic field does not act as a protective barrier against such occurrences, hence it is crucial to highlight that this gap did not allow beings from other dimensions or planets to enter. Instead, it protects the Earth from the strong solar winds as its main purpose. The Earth's magnetic field, along with the ozone layer, is crucial in reducing the negative consequences of solar activity. If solar winds aren't controlled, they could have disastrous effects like destroying the ozone layer. These winds are also to blame for the captivating auroras that may be seen in the sky. Although from Earth these natural occurrences seem beautiful, they actually pose serious risks to satellites, electrical grids, and spaceborne operations, which might result in widespread blackouts. NASA therefore keeps a close eye on the Earth's magnetic field, and recent observations have shown a notable decline in its strength. The South Atlantic anomaly, which spans South America and Southwest Africa, is of particular concern. A vital force in preserving the planet's equilibrium is the magnetic field of the Earth. It makes it possible for compasses to correctly point north and makes it easier for animals to navigate during lengthy migrations. Additionally, it protects our atmosphere from the damaging impacts of solar winds, highlighting its crucial role in maintaining the quality of life on Earth. Weakened patches may have resulted from the superbeam collider being turned on, although this is not clear. The occurrence involving the broken magnetic field line, however, points to a connection. These vulnerable regions present a serious risk, especially to satellites and other orbiting vehicles. Satellite technology is significantly used in communication systems that are essential to the modern world, including telephones, radios, televisions, and the internet. This craft will be more vulnerable to the effects of solar flares than people are as they become more frequent. In addition to releasing heat, light, and radiation, solar flares can cause coronal mass ejections, CMEs, which are enormous eruptions on the sun's surface brought on by magnetic field instability. Elon Musk's loss of 40 SpaceX satellites during a solar storm in early 2022 served as evidence that CMEs can cause widespread outages and interfere with communication infrastructure. These storms are moving quickly toward Earth and carrying heat and electrical charges. While they can produce amazing displays like the Northern Lights, they can also cause trouble and pose hazards. Two enormous flare outbursts have lately been reported by NASA to be moving toward Earth at a pace of around 2 million miles per hour. If a storm develops, we might face problems with satellites, global internet disturbances, radio navigation frequency disruptions, and other issues that might cause trillion-dollar damages. The devastation caused by solar storms is illustrated by historical occurrences like the Carrington event in 1859 and the Quebec incident in 1989. However, they also provide breathtaking sky decorations. The recent turn of events raises the prospect of encountering such a storm once more. The magnetic fields of the Sun and the Earth are still mysteries to science. The employment of the Large Hadron Collider, LHC, may have exacerbated the magnetic field system's weaknesses, opening the door for solar winds to enter. There have been theories that CERN has opened a doorway to another dimension. Although these theories are unproven, worries regarding the LHC's effects have remained ever since its debut in 2008. To prevent a dark day for humanity, it is essential for scientific societies, including CERN and other research institutions, to work together in reducing the risks connected with impending solar storms. With that, we have reached the end of today's show. What do you think of LHC's latest discovery? Would it be able to detect the antimatter in the future? Do let us know your thoughts in the comments section below. If you enjoyed this video, please hit that thumbs up. It will help us to understand our audience and allows YouTube to suggest similar videos to you. Thanks for watching. We hope to see you at the next one.